Hello pre-calc honors students, here we are with the formal definition of limit. And it gets a little tricky and there's some new terminology I want you to get used to it. First of all, before we get into the definition, some symbology. And that is, an upside down A means for all. And a backwards E means there exists. This comes up over and over again in the shorthand definition for the limit. And let me write this a little larger now. The formal definition of the limit as x goes to c of f of x is equal to L if the following statement is true. Now, limit's trickier than just saying, oh, let's just put c in and say it's equal to f of c. We're often going to find that the function itself behaves in one way, but right at that point x equals c, the function doesn't exist. So we want to get an idea of the trend as we get closer to that function. So, given any epsilon greater than 0, however small, there exists a delta greater than 0. There's the abbreviation for it. For all epsilon greater than 0, there exists a delta greater than 0, such that if 0 is less than x minus c is less than delta, the absolute value of that, then the absolute value of f of x minus L is less than epsilon. Basically, this is saying if x is within delta of c. So that means x is getting close to c. It's within delta. It doesn't have to actually be at c. Notice the definition says 0 strictly less than. So basically, x is going to range between c and delta plus c, or the opposite. Then f of x, which is the y's, is within epsilon of the limit. So as the x's get close to c, the y's will get close to the limit L. Okay? Let's see how this works now. Let's use the definition of limit to prove this. Basically, we work backwards from f of x minus L less than epsilon. We want to always be within epsilon of the limit. And how far do you have to go to do that? So you're going to show that for all epsilon, no matter what we pick for epsilon, we're going to pick delta in this case to equal epsilon over 4, and then we'll get that close. So we start with the absolute value of f of x minus L is less than epsilon. Okay? Simplify that down. In this case, f of x is 4x minus 5. L is 3. And that means an absolute value of 4x minus 8. Factor out the 4. We can distribute absolute value over multiplication. So it's 4 times the absolute value of x minus 2 is less than epsilon. Divide both sides by 4. It doesn't change the direction of the arrow because it's a positive number. So therefore, the absolute value of x minus a, remember, is less than delta. Those are the two key parts, or x minus c in this case, as x approaches c. So, if we pick delta to be epsilon over 4, we'll always guarantee that our limit will get within epsilon of, our function will get within epsilon of the limit. Let me show this to you on GeoGebra so you get a visual idea of what's going on here. Here's the idea. Oh my gosh, GeoGebra's freaking out again. There we go. Here we go. In purple is the function 4x minus 5. And b here is a point on the function. I'm sliding this along. Now notice what the blue represents here. As x gets closer to 2, and in blue here that's delta. Delta is basically the error in x. And as that gets closer to 2, as that gets small, then our point is going to get closer and closer and closer to 2. X will approach 2. As that happens, f of x approaches 3. And now epsilon here in red represents the gap between the y-coordinate of the point you're looking at and the limit that you're trying to get to. And notice in this case we actually do get to the limit right at x equals 2. But as we go on either side of it, we can see that we've got some error in x and some error in y. That's basically the difference between delta and epsilon. And that's why they're called delta epsilon proofs. Now, so if someone comes along and says, hey, can you get within 1 of the limit? We're claiming that the limit here is 3. Well, right now we're more than that away. We're 1.1 away. So all I have to do is move this in closer. Now we're within 1. So we just had to make our delta smaller. Now let's say I want to get within a half. So I move in a little closer and I pick delta to be even smaller, and I'll get within a half of the limit. Now notice this ratio of epsilon over delta is always 4 no matter where I am. That's because it's just a straight line and it's got a slope of 4. Okay? All right. So basically, let me emphasize this a little more. This, basically in red here, is our epsilon. And in blue, that's delta. And if we want to get within a certain epsilon of the limit, we must pick delta to be of a certain size small enough. In this case, we pick delta equal epsilon over 4, no matter what epsilon is. Okay. Let's try another example. Here, determine delta for the given epsilon such that fx minus L is less than epsilon, whatever 0 is less than x minus c is less than delta. So we start with the absolute value of f of x minus L is less than epsilon. We want to make this happen. We want to get within epsilon, in this case 0.01, of the limit. So we put in f of x, which is 2x plus 4, we subtract off the limit, which is 10, and make that less than epsilon. So absolute value of 2x minus 6 is less than epsilon. So absolute value of 2 times x minus 3 is less than epsilon. So absolute value of 2 times absolute value of x minus 3 is less than epsilon. So 2 times the absolute value of x minus 3 is less than epsilon. So the absolute value of x minus 3 is less than epsilon over 2. So we pick delta to equal epsilon over 2. And in this case, since epsilon equals 0.01, we can pick delta to equal 0.01 divided by 2, and we get 0.005. So what we're saying is, if I want to get within 0.01 of the limit here of 10, that is between 9.99 and 10.01, I'll have to get this close to 3, within 2.995 and 3.05, in that range, in order to get that close to the limit. Now right here, we proved it in general. If we said pick delta equal epsilon over 2, and notice how that's associated with the slope of the line. Here we proved it for a specific value of epsilon. Let's try another limit. The limit as x goes to 2 of 4x minus 5 is equal to 3, and pick epsilon to equal 0.001. So we start with the absolute value of f of x minus L is less than epsilon. So 4x minus 5 minus the limit, which is 3, is less than epsilon. So absolute value of 4x minus 8 is less than epsilon. We can factor out the 4 and take its absolute value. 4 times the absolute value of x minus 2 is less than epsilon. So the absolute value of x minus 2 is less than epsilon over 4. So we're going to pick delta to equal epsilon over 4. In this case, epsilon equals 0.001. So we pick delta to equal 0.001 over 4, and we get 0.00025. So if we get that close to 2, we will get 0.001 close to 3. That's it. Flange out.